Hello everybody. Today we shall start a complete new section which is about special relativity. We'll not learn a lot of special relativity in this course, but we are planning to learn the basics of special relativity very well. And that's our goal. And we will start from a kind of historical perspective where I'll first discuss what is the crisis in physics that existed as we are turning from 1800s to 1900s and how it was resolved. So, the first two lectures will essentially discuss this crisis and its understanding, and then we'll bring in special relativity and see how it solves many of the problems and what are the new things that it gave to our plates or dinner plates. I'll request you to be very, very attentive in these lectures in special relativity. It is very easy to confuse things in special relativity, and it is also very easy not confuse things in special relativity if you look at it from the right perspective. So please come in a journey with me and follow the lectures quite meticulously. You can have doubts, you please note them down and we should discuss them thoroughly. Okay, so let us start. First question we ask today is how we do physics. So what do I mean by doing physics? What do I mean it by writing down a physical law, etc.? So the first question, basic question we ask is how to do physics. Remember, physics is one of the natural sciences, which means we are trying to explain nature and trying to predict things out of our experience that we have grabbed from the nature, right? So how do I do it? The physicist has come up with this very nice method. So what they do first is they find the law of nature. Find the law. And obviously, finding means you know it by yourself. That is not good enough if you want to communicate with somebody else. So you have to write it down. And it is not literally writing it down, it means giving it a form of mathematical structure. And that mostly we can do from the perspective of one reference frame. So write it down in a given reference frame. I guess you have enough idea about what I mean by a reference frame, but still let us spend a little bit of time here where I try to explain to you what I mean by a reference frame. So, a reference frame, and we let us think about it by example. For example, so let's say that there is a train, and I draw train this way. You will see that I am drawing train this way many times. I'm not a good artist, so this is the best I can represent a train. And what you are doing inside the train is just throwing. So you are sitting here inside the train, and that's how I draw a person. And let me put a magnifying glass and magnify myself. I'm sorry. So I should have used this. So I magnify myself here. What I'm doing is I'm sitting there and I'm throwing a ball up and down. The ball is going up and coming down, going up and coming down. That's all I'm doing. Okay. Now, as you are sitting there in the train, whether the train is moving or not, what you will see is that the ball is going up and falling exactly in your hand, right? As I assume that the train is moving at a constant velocity, you will always see that the ball is going up and coming down in your hand, going up and coming down in your hand. So that is the perspective of your reference frame. Say your friend is seeing you moving with the train. Train is going obviously with certain velocity, and for your friend who is standing here, see you moving with the train. Now for him, when you threw the ball up, so that maybe at this point, with respect to him, so at this point you threw the ball up, obviously the train was, so you were standing there, the train at that point of time was something somewhere here when you threw the ball up, and where I have drawn it with a blue, then the ball comes down. So here is where the ball comes down. So what your friend standing alongside the track will see is the ball goes up and then come down. It goes up by exactly the same amount you threw it up from your reference frame, but then he will see not it going vertically up and coming down, he will see a kind of angled trajectory, right? So this is what we will obviously see differently, the same phenomena that I throw the ball up and it comes down to my hand. I'll see the same phenomena from two different reference frames a little differently. Which means if I want to write down a mathematical form, which is, say, you want to write down the trajectory of this ball, that has to be written down from a given reference frame. If I want to generalize it, I say I cannot write it down from all reference frame. For different reference frames, the trajectory of the ball actually will look different. Imagine another train going past you from the other direction. You will see it happening even faster in your hand. So the first thing that a physicist do is to find the law of nature and write it down in his preferred reference frame. And I also said that give it a mathematical structure. And we have already seen in our course that when I say mathematical structure, I essentially mean, for most of the cases in physics, a differential equation. A mathematical structure is essentially a differential equation. What have you learned about it? So you have learned several differential equations like the Euler-Lagrange equations, or you may have called it Lagrange equations, same thing, or the Hamilton's equations. Right? So these are the different mathematical structures in which I write down the laws. Okay, so that is the first step that a physicist do. to do physics. But that's not good enough. You see, if you write down the law, you find out the differential equation, solve it, you get the trajectory, you know how your ball is behaving, which you are throwing up and coming down to your hand as you are moving with the train. But how will your friend figure out who is standing alongside the track how the ball is behaving? So, what I need to do is to figure out, given this trajectory in one reference frame, how do I go to the trajectory in a different reference frame? So, how do I go from there to here? So, that is what I have to figure out. So, for that, the physicist uses the second thing in our list is that figure out how to write the same law or any consequence of it, obviously, like the trajectory is the consequence of the Euler-Lagrange equation. If you solve it with the nice initial conditions, you get the right trajectory in any other reference frame. So you have figured out, as a person sitting inside the train, how the ball will behave with time, how will it go up and fall down. But you have not completed there. You also have figured out a relation. Once you know it, how the ball will behave as a function of time in your train, how anybody else in any other reference frame will know it, will calculate it. So that is the second part. And this is achieved by coordinate transformation or reference frame transformations. Right? So this is how you do it. And we'll just shortly we'll talk about one example. Maybe the same example. We'll do it clearly here. So let's say how do we do it? Well, in this case, let's say that the motion of this direction is our x-axis. The velocity of the train is along v, so let's call that vx. Okay, the velocity of the train is along v, it's called vx, and let's call the coordinate of me, who is sitting inside the train, as x, and the time I measure for anything to happen is t. So when I am throwing up, I measure t1. When I catch the ball back, I call it t2, etc. Similarly, for this person, let us call, he measures these two distances, right? So this is one, this is the other one, this is along x. So these two distances for this person is x prime, and let us call this time t prime because it's another person. Just give it another name, nothing more than that, more or less. Okay, and if I ask the question, how is x prime and x related and t prime and t related? You know that how they are related. So t prime is always t, time never changes between these two. All if I whether I watch, whether I have a watch here or I have a watch here, I mean they are good watches. I'm not saying that they are running slow or anything, but they will measure the same time. And the other thing is that the position I know that this person will measure a little extra position with respect to this person because of the velocity of the train. So the train is moving. So if I call x prime, so x prime will be x plus vt. So let me correct myself. Call this vxt. So vx is the velocity of the train, and I'm assuming a constant velocity. Now, I said that I'm assuming a constant velocity. That is for a reason. Here in the second thing, we said that figure out how to write the same law of nature in any other reference frame. And it was Newton who realized that he could not do it, so it could not be done. The Newton's laws of motion that you have read or studied, once you have written down in one reference frame, you cannot translate those laws to any other reference frame. You can only translate those laws to those reference frames which are inertial reference frames, right? So this is possible only for inertial reference frame. Today we have figured out how to do it even for non-inertial frames, but it's a lot complicated physics and we are not going to discuss it in this course. But all our discussion are then limited to inertial reference frames which are moving with respect to each other with constant velocities. The velocity never changes. So this Vx is constant. Constant means it doesn't change with time. Okay, and because it's moving along x-axis, so y and z coordinates of things will not change. These more intuitive, and we have used this. So, like you have studied s equals to s0 plus vt. So that's essentially x prime equals x plus vxt. It's the same expression written in different ways. Now these have a name. These are called Galilean transformation rules. And Galileo found these out by experiments. Okay, so these are called Galilean transformations. Let's try to apply Galilean transformation once. Let's ask the question: what is the velocity that this person will measure, and what is the velocity that this person will measure? So this say that this person measures a velocity along x direction as vx, and this person measures the velocity as we are doing always vx prime. Okay, so he throws something now in the x direction. He throws something in the x direction. So maybe you are throwing a ball to the wall of the train, and it throws with a velocity vx. If this person measures the velocity from outside the train, what is the velocity that this person of that ball he will measure? And that I said is vx prime. Now velocity we know what it is. So vx by definition, vx is rate of change of x with respect to t, and vx prime is rate of change of x as measured by the person outside with respect to the change in time as measured by the person outside, right? So let us try to calculate what is vx prime here. So Vx prime will be dx prime. If I take differential of this expression, I get dx plus, remember that capital Vx is the velocity of the train, which is supposed to be constant for us to have inertial reference frame, times dt, and dt prime is same as dt, so this is just this. So you get Vx, dx by dt is Vx, that's the first term, and the second term dt cancels out, this is just this. And that's our well-known velocity transformation rule. It's a Galilean velocity transformation rule because it comes by application of Galilean transformation. Right? This is also well known and you have used it in your class 2 a lot. This is where from it comes. Okay. So now we know what we mean by saying that how we do physics. We find the laws of physics, laws of nature, write it down in a mathematical form in a given reference frame, and then we figure out how to write the same laws of nature in any other reference frame. For example, these are the Galilean transformations that we talked about that tells you how the coordinates transform. And from that, we have also derived if I have a velocity, how will it transform? Right? So, this is the understanding of physics that we have so far. Now, in the first part of your course, you have dealt with a very particular type of physics problems, which are mostly dealing with particle trajectories given by Euler-Lagrange or Hamilton's equations of motion. So there what changes is the position or the velocity or the momentum of the particle, right? But there are other things also of which we do physics, and one of them is called waves. So let us discuss it a little bit now. Waves. So what are waves? Remember that we can call it like, it's not a definition, by the way, it's not a sacrosanct definition. Loosely we can call it a disturbance in space and time both in this case. Disturbance of what? Well, that will depend on what is the wave of. But let us first discuss a very general wave. I'm sure you have studied this in plus 2, but there is no harm in discussing it again. Okay, so let's call, so it has to be a disturbance in space and time. So whatever being disturbed will be a function of two variables. Let's call it psi. Okay, so this is what is being disturbed, and let us call it a function of x and t. Okay, and we know that a solution for such a case is some a, some amplitude of the wave, and I can have then cosine or sine of something which is where I have the wavelength lambda, and then I have the frequency nu, and that's how we depend on x and t, right? And we also know that for such a wave, if the wave velocity, so the wave velocity we call, say, v of wave, I have wavelengths which I have written here as lambda, and I have frequency. which is nu, right? And we know that these three are related in a certain way. V is lambda times nu. So this also you have studied. This can be written in a little different ways also, as you know that we can define k, which is 2 pi by lambda, and we can define omega, which is 2 pi nu. Then in terms of these two, we can write omega as the wave velocity times k. Now these things depends on, these relations are not very sacrosanct. This depends on what type of wave you are looking at. The more uh, familiar wave that you have studied is where these relations are valid. These have a name. These are called dispersion relations. And we'll have a detailed discussion on dispersion relation when we'll come to the study of quantum mechanics. Okay. Now, all right. So far, so good. So what we have described here as the disturbance, which is the wave of, is essentially like the trajectory in our problems in mechanics. In problems in mechanics, we have solved a differential equation, Euler-Lagrange equation or Hamilton's equation, and found the trajectories, which is how the position or the velocity or the momentum depends on time. Here, how the disturbance, which is psi, depends on x and t, is like the trajectory, trajectory equivalent in case of wave. So as we said that we usually write down physical laws in terms of a differential equation. So there should be a differential equation which gives this solution. And it turns out there is one, and there can be many different types of equations for a wave. But one equation which we are very familiar with, in which happens in many cases, is the following. So we call it wave equation, and it looks like this. Let me write it down and then explain to you. So I guess you are now familiar with partial derivatives. So when I take del psi del t, that essentially means that I take a derivative of psi with respect to time. But psi is also a variable of x. So when I take the derivative, I keep x constant. I don't do anything with the x. So similarly, when I take a derivative of psi with respect to x, I don't do anything with time. I just take the derivative with respect to x. Okay. So this is how the wave equation, which will as a solution give you a wave like this, look like. And let us have a try. Let us try to put psi, which is this, back into this equation and check if this actually gives me the wave equation. This actually is the wave equation. So for that, what I do, so I calculate del psi del t first. And remember how we calculate del psi del t? We take a derivative of this with respect to t, and we don't even care about x. So if I take a derivative, cos will become sine, and that will come with a minus sign. But and then when I take a derivative with respect to t, I will get a minus 2 pi nu in front. So I will get plus 2 pi nu, two minuses cancels out, and a, and then sine of, right? So that is once, but I have to take the derivative with respect to time two times. So when I do it second time, now sine will become cos, and I will have that minus sign. So 2 pi nu whole square. I will get another 2 pi nu out now, and a. So I essentially I get a cos. Let me write it down once for you. 2 pi x by lambda minus 2 pi nu t. If you look at it carefully, a cos 2 pi x by lambda minus 2 pi nu t is essentially our psi, as you can see it here. So I can just write it at this times psi. Or you will agree that 2 pi nu is nothing but omega, so this is omega square psi. So that is the derivative in the left hand side of the equation, and I leave it to you to do the same for the right hand side of the equation. And if you do, what we'll get is k square psi. Okay. So now if I put these back in my wave equation, 1 by v omega square, del 2 psi del t2 is minus omega square psi, and the right hand side I have minus k square psi. The 2 minus I am not writing, and of course psi also you can get rid of. So what you get is get back this, which is nothing but my dispersion relation, right? So we said that this is a solution, this is a wave given this dispersion relations are correct, and that's what we have got back from this wave equation. So this is equation for a wave. So when I say that I will write down the physical laws, what I will do is for a wave is essentially I will write down this equation and then solve this to get the wave solution. This is one of the solutions. Obviously, there can be many other solutions, as we'll see later. But what have we learned now? What will be an example? So example is a simple example of a wave. Sound is what comes into the mind, and what coming to you right now from me. So what is the disturbance of psi is essentially either you can call pressure in the air or the density of the air. So these two gets disturbed as I speak, and that causes the sound wave which reaches you, and you are able to hear me. Very nice. Do you know that? So you have also studied this lot of instruments. You have studied a pipe which has, say, both ends open, and you know that it has a fundamental mode which looks like this. This is essentially how a flute works, right? So you know that there is a node here where the disturbance is 0, and there are antinodes or the maximum disturbance at that either end, and this constitutes, if the length is L, length of this pipe is L, then this will corresponds to a wavelength lambda, which is 2 times the L. So it creates a vibration of a wavelength lambda, which is 2 times the L. So if the speed of the sound wave, if I call it Vs, so sound wave speed or sound wave velocity, more appropriate. So this is from our dispersion relation is lambda times nu, and lambda is fixed because of the L, the length of the pipe. So I get a vibration of a certain frequency, right? And that is how, so when you say you are playing a musical instrument, you have certain frequencies which you have to play. That is how you play a certain frequency. However, you see that the relation between nu and lambda is this. So if I change the speed of the wave, the frequency will change. So if the sound is being produced by a moving object, just like we talked about we talked about this person sitting in the train, the sound is produced by him and I'm listening from outside, then I will see the frequency of the sound changes. This is what you have learned as Doppler effect, right? When the train comes towards you, you hear one frequency, and when the train goes away from you, you hear a little different frequency. This is essentially because of this. So which means the speed of the sound wave changes if you look at it from different medium or different reference frame. So for different reference frame, the speed of the sound wave which sits here will be different for sound, which we also see in Doppler effect. So it's a real phenomenon. So what I have to do, the second part of the physics, I have written down the differential equation, which is the first part. The second part, I have to tell you how this speed of sound will change between different reference frames, and that I can do using the Galilean transformations. So what will you use? You will use the Galilean transformation of velocity, as we have figured it out here. And then I calculate the new frequency that the person who is standing outside near the train track will listen. And that's absolutely all right. That's how you have calculated the Doppler shift formula. There is no difficulty here. The real difficulty came in, and that is the crisis of the physics that we are talking about today, is with the theory of electricity and magnetism, or we call it electrodynamics. It is not developed by a single person, but it was realized in its full glory by James Clerk Maxwell. And he did so in 1860s, not in 1860, but in that decade. Okay. So what he suggested is that this also you have studied, that light is a wave. What is disturbed in this wave is the electric field and the magnetic field. How do you write down the physical laws? in terms of a differential equation. And though this is not the direct physical law or the direct differential equation that comes from Maxwell's theory of electrodynamics, but it's a consequence, and the consequence is the equation for the light wave. It looks like this. The speed of light is written as c, and it's exactly the same differential equation. Now, either on electric field or magnetic field, I'm just writing for E. And remember that electric field and magnetic field both are vectors. So there can be many other component. And in general, it's a wave in 3 dimension, not only one spatial dimension. So there can be more complications, but in the simplest form, this is the equation for the light wave. Just like the equation for the sound wave. And what is vibrating here, the disturbance is of the electric and the magnetic field. Now, so far, so good. There is no problem here so far. But it turns out that the quantity c, which is the speed of light, is related to the quantities of electricity and magnetism in this way. These are the quantities comes from properties of free space, or let me call space. And when I say properties, it means electric and magnetic property. Now it is like mass or charge kind of thing. It's at a little more fundamental level, but let's not go into so much detail right now. But it's a property of the space, free space. Free space, I am emphasizing, I should write here free, and that is what that zeros, epsilon naught and y mu naught, those zeros stands for free. Okay. If it goes to a medium, obviously it changes, but we are talking about when it is going through free space. There is no medium. So for the light wave, for the electric and magnetic fields to vibrate, there requires no medium. So what is the problem here? The problem, the crisis in the physics now is that these quantities then should depend, if I believe in Galilean transformation, on which reference frame I am looking at, I'm sitting. But we know that mass of an object or charge of an object, these are properties of the objects, and this epsilon naught mu naught are properties of free space. So apparently they should not depend on which reference frame I am looking at, whether I'm inside the train or outside. So people postulated that there is, so this is a postulate. So let me write this as a postulate, and this is called the ether postulate. What does the ether postulate tells you? The speed of light, or there exists a hypothetical because a postulate or a hypothesis is introducing it, medium that is there in everywhere, that is there everywhere in the universe. with respect to this medium, light travels at constant speed, very specific value it has. So if I want to go to any other medium, then I have to use Galilean transformation. For any other medium, would be calculated using okay. So this was the postulate, the ether postulate that was bring in to discuss the speed of the light. Okay. Now what we will do in the next lecture is to see what consequence what that we should observe if this postulate is true, and then what comes out of experiments which were used to observe the effect of this ether postulate. So I'll stop here today, and we'll continue from here in the next day.